All right, sorry about that. The projectors in the classroom were having a panic attack. So anyway, I'm going to ask you guys what I hope is a fairly simple question. If we had a DC circuit, how would we measure power? Yeah. Measure it. We'll both measure and calculate, right? Sure. So what Matthew has suggested is, let's say that we had a DC network. We don't really care what's inside of the network. Overall, we would just want to know how much power is being absorbed by this network. And it's part of a larger circuit. So what Matthew has suggested is that we could put an ammeter in series with the network. And a voltmeter in parallel with the network. And the power absorbed by the network would just be whatever the reading of the ammeter is. So some current I, and whatever the reading of the voltmeter is, some voltage V. Absolutely right. So that's how it would work for a DC network. Now, why won't that work for an AC network? If you got a multimeter from up here, you could measure RMS value of the voltage drop across the network and the RMS value of the current. But why isn't that the average power? So if I have the magnitude of some RMS voltage and the magnitude of some RMS current, because that's what my multimeter can measure, when I multiply those two numbers together, what do I get? Apparent power. Absolutely right. That is the magnitude of the complex power, or the apparent power, okay? Which is very much not the average power, okay? So in an AC circuit, we need to use a specialized piece of equipment, which is called the wattmeter, okay? So let's say that I had a simple AC circuit. Here are the terminals of the rest of the network. Here are the terminals that are connecting to my load impedance. I don't particularly care what this load impedance is, so I'm just going to represent it by some impedance ZL. I would put a wattmeter in between the rest of the circuit and the load that I'm trying to measure. So a wattmeter is a specialized device that consists of two coils. So we're going to have a coil up here, and the polarity of this coil is important. And then we also have a coil here. The polarity of this coil is important. And these two coils oriented in this particular configuration form what is called a watt meter. Okay. So the coil on top is the current coil. and it senses the current flowing through it. The coil here is the, let me write this better so that you can see it's supposed to be potential, but cram it in. Potential coil like so, and it gives us some reading on the voltage. And then what we're going to see is that it's going to, those voltages and currents are going to cause a torque on a needle effectively that moves it some fixed amount based on the amount of power, right? So our watt meter is an old school analog device that has a view meter, and wherever this needle points is how much power, average power, our device is absorbing. So that's how we would configure a watt meter for a single phase system, okay? Now let's look at how we might utilize a watt meter in a three-phase system. So let's say that I have for the sake of argument, a Y connected load. So, and I wanted to connect a watt meter to measure the power over, let's just say one phase. So if this were, let's talk about that for a moment, actually. Excuse me. So if this were a balanced load, if I were able to tell the power over one phase, then I could simply multiply that number by 3 to get the power over all 3 phases, right? So I could make an accurate measurement with a single watt meter. So in this particular configuration, for our Y connected thing, we would need to figure out how to connect our watt meter. So something like this is our sense coil here, or our current coil. And then we would need to tie our voltage coil over here to the neutral, so that we're measuring the phase current and the phase voltage, because we need both of those quantities in order to calculate our average power. Or we could do line current and line voltage, but then we'd have to deal with the fact that it's going to be a square root of 3 relation, excuse me, square root of 3 relationship instead of a 3 times the measurement type thing, okay? Quickly. So if we had the power from our watt meter, let's just say that it came out to be 100 watts. How could we, so let's say that we had a watt meter on hand and we also had a multimeter so that we could measure current and voltage. Our watt meter is going to tell us the average power. How can we figure out what power factor the load is operating at? So the average power is given by the watt meter. So that's something that we can measure. So what are two other quantities that we can measure so that we can figure out the apparent power? The voltage and the current. Absolutely right. Right. So if we put a current meter in series and a voltmeter in parallel, let's say that the measurement of our voltmeter was, why is this working? 118 volts RMS, and the measurement from our ammeter or our current meter was 2.5 amps RMS. What information could we get from this? So we could get the apparent power, we know the average power, so we could get the power factor, right? Our power factor in this case would just be P over V times I, the reading from the voltmeter and the reading from the current meter. From that, we could get our power factor angle and all that kind of good stuff. We wouldn't know necessarily whether it was positive or negative, but we could take an educated guess on if we knew something about our load. So if it were a motor, the angle would probably be positive because the overwhelming majority of motors that we're going to see are induction motors and things like that. But we have enough tools here with a multimeter and a wattmeter to figure out a lot of different physical characteristics of the power that's being absorbed by a practical machine. Okay. Now, as I mentioned a moment ago, if we have a balanced system, this is all we need. What if we didn't have a balanced system? We'd have to use 3 wattmeters, one for each phase. Okay. So I could throw another wattmeter in here. Like so. So this would be the A phase thing. Throwing, and let me make sure I'm remembering to do the polarity of the coils. Once again, that is important. Right. And we'd also obviously have to put in a current meter and a voltmeter for each of the 3 phases as well. And then from there, we could figure out power factors and all that kind of good stuff. But if we were just interested in the total average power consumed by the load, because we were trying to figure out how to feed this thing using wires and all that kind of stuff, 3 watt meters would get the job done, right? So there is a little bit of a problem here currently though, okay? And we could, so the problem is we're measuring the phase current using our wattmeter, or the wattmeter is able to take in our phase current and it's able to measure our phase voltage here because of the way that it is connected, right? The problem is that in not all pieces of equipment are we going to have access to this neutral terminal. So for instance, in a 3-phase induction motor, we are only going to have access to the line terminals A, B, and C. The neutral point where all things are connected together is literally internal to the machine, and you probably don't want to have to take the whole thing apart to connect a meter there and then put it back together and run it and hope that everything is okay. It'd be vastly expensive and complicated to do that. So are you suggesting that we tie the 3? So let me rephrase. Right. But where's ground in a 3-phase system? So if I drew a 3-phase system, oops, sorry, let me pull this up. So let's say that I have a 3-phase source here And over here, I have three-phase load. Where's ground? There isn't one. So that's the problem, right? Our neutral could be tied to a ground. For the neutral conductor, the neutral conductor for our source may be tied to ground. It doesn't have to be. The neutral conductor for our load probably isn't. So ground is a physical connection to earth ground. Neutral is just a conductor that we're using as a reference. And I am saying that we don't necessarily always have access to that neutral. Right, so we physically do not have access to that neutral. So therein lies the problem, okay? So effectively, the problem that I'm trying to describe here, and I think I'm doing it poorly, is that we have to have access to the internal workings of the machine in order to imply, or for some machines, we might have to have access to the internal workings in order to apply 3 watt meters. At least that's how it looks in a a Y connected system. So what if we had a delta connected system? Maybe things would be slightly easier for us, right? So if I had a delta system, draw this, giving myself enough room. Once again, I'm going to want my watt meter connected in such a way that I am measuring phase quantities, or the watt meter is seeing phase quantities, I guess would be a better way to put it. Right. A, B, and C. So if I were trying to connect 3 watt meters to this thing, and I'm trying to measure my phase current and my phase voltage, well, we're going to run into that same problem of we have to have an internal connection, because our phase current is inside the device, right? So we have access to our phase voltages from the terminals, but we don't have access to our phase current unless we literally crack this open and put the current coil between these 2 points on each phase, right? So we're running into yet another problem, right? So 3 watt meters would be great if we have access to the internal workings of whatever we're trying to measure, but in a lot of situations, we are not going to have access. So instead, what is done is what's called the 2 watt meter method, okay? So over here, I'm going to represent a balanced 3-phase source. And let's put it over here. This will be a 3-phase load. Now, I want to be very clear here. It does not matter if the load is delta or Y, and it does not matter if the load is balanced or unbalanced. Okay. So what I could do here's lowercase a, capital A, lowercase b, capital B, and lowercase c, capital C. I can connect a wattmeter across the A and B phases. And I can connect a second wattmeter across the C and B phases. Like so. So I have two wattmeters connected. This wattmeter up here is going to be measuring a current I'm going to call P1. And this wattmeter down here is going to be measuring a current I'm going to call P2. So I'm going to identify a couple of things here while we're at it. So our current coil for our top wattmeter is experiencing the line current IAA, and it's also seeing the line to line measured voltage VAB. Our current coil for our bottom wattmeter is seeing the line current ICC, and it's seeing the line to line voltage VCB, right? So the power that is being measured by wattmeter 1 is the magnitude of the voltage VAB multiplied by the magnitude of that line current IAA times the cosine of some angle theta 1, where, we put it out here, this angle theta 1 is the difference in the angles between VAB. So this is theta for VAB minus theta for IAA. Very similarly, wattmeter 2 is reading, excuse me, the magnitude of that voltage VCB, the magnitude of that current ICC, cosine some angle theta 2, where theta 2 is the angle of theta VCB minus the angle of theta ICC, right? So we could rewrite these equations a little bit here. So VAB is a line voltage, right? It's a voltage drop measured across the transmission line terminals. So its magnitude is just going to be VL. IAA, by definition, is a line current, so its magnitude is going to be simply IL, assuming we have a balanced system here. And then cosine theta 1 and P2 is going to be VL IL cosine theta 2. So what we're going to do now is we're going to figure out how we can express those angles theta 1 and theta 2 in terms of the angle of the impedance. Right? Anybody have any thoughts on what that might be? So let me go to another page here really quickly. We're going to figure this out. Let's say that we had a Y connected load, ZY like so. Where ZY has some magnitude and it has some phase angle theta ZY, right? Here's our voltage VAN. Here's our current IAN. Here's our current IAA. Here's our voltage VAB. So just to be clear, these are the two things that we have access to when we have a watt meter. Now we're trying to figure out the relationship between the difference of the angles between those two quantities and the difference of the angles between the voltage drop across our impedance and the current flowing through our impedance, right? So ZY, by definition, is VAN over IAN, right? So from this, the angle of ZY is just the angle of VAN minus the angle of IAN. How is the line current IAA related to IAN? Look at the diagram. For this Y connected load, how are IAA and IAN related? They're the same thing. So that means the angle of IAA is equal to the angle of IAN, right? How are VAN and VAB related to each other? Yep. So we know that VAB is equal to VAN times √3 angle 30 degrees, which means the angle of VAB is equal to the angle of VAN plus 30 degrees, right? So if theta 1 were equal to the angle of VAB minus the angle of IAA. That's going to look like the angle of VAN plus 30 degrees minus the angle, excuse me, the angle of IAN, or simply the angle of ZY plus 30 degrees. So in this Y connected system, theta 1 is just the angle of the impedance plus 30 degrees. And if we did it for this guy down here, it'd be the angle of the impedance minus 30 degrees because we swapped the polarity. Okay. What if we had a delta connected load, right? So we figured out what the relationship is for a Y load. Let's look at a delta load, right? So here's Z delta. Here's another Z delta. And third Z delta. Here's our voltage VAB. Here is our phase current IAB. Here is our phase current, or excuse me, our line current IAA, right? So for our delta connected impedance, that's still just the magnitude of Z delta with an angle of theta Z delta. And we could say that our delta connected impedance is just the ratio of our phase voltage divided by our phase current, which means the angle of our impedance is theta VAB minus theta IAB, right? So because our line voltages and our phase voltages are the same thing, we don't really need to do any conversion with regards to that part. So now we're going to have to look at our currents, right? So what's the relationship between IAA and IAB, Bailey? Because this was what you were trying to tell me earlier. Negative 30, right? So IAA is equal to IAB times √3 angle negative 30 degrees. We derived that multiple times and used it in homework problems and example problems and all that kind of good stuff. So we could say that the angle of IAA is the angle of IAB minus 30 degrees. Recalling that theta 1 was the difference between the angle of VAB and the angle of IAA, that's going to look like the angle of VAB minus the angle, of IAB minus 30 degrees, which is the exact same thing as the angle of the impedance plus 30 degrees. So it does not matter what configuration we have, whether it's a Y or a delta. Up here, this is just the angle of the impedance plus 30 degrees, and this is the angle of the impedance minus 30 degrees. So what would happen if we added P1 and P2 together? So we would have VL IL cosine theta z plus 30 degrees plus VL IL cosine theta z minus 30 degrees, which, using a little bit of trig, which I'm not going to make you guys suffer through, just to be clear, would come out to be twice, this thing will write, VL IL cosine theta z cosine 30 degrees. So what is 2 times the cosine of 30 degrees? You have calculators? Square root of 3. I'll be damned. What is this equation? Total average power in your system. So by only using 2 watt meters, we're actually able to figure out what the total average power is because of the relationships between things. Okay. So 2 watt meters, no internal connections whatsoever. Everything is connected between the transmission line terminals, which means we do not need to have access to anything internal to the load that we're trying to measure. And just for the fun of things here, if we take the ratio of P1 to P2, that's going to look like the cosine of 30 degrees plus the angle of our impedance. Actually, let me do it this way around. Theta z plus 30 degrees divided by the cosine of theta z minus 30 degrees. And manipulating this, we could find that the tangent of theta is equal to the square root of 3 times P2 minus P1 over 2 plus P1. Why is this important? It allows us to calculate our power factor angle and therefore our power factor only using the watt meters, which means we don't even need multimeters anymore to figure out any possible thing that we could need about a balanced 3-phase load. Yes. That is the theta S, so the power factor angle. Our power factor angle will also be the angle. So are you, sorry, you were asking about if it was theta Z? Yes, it is the same thing because theta S and theta Z are by definition going to be the same thing. So yeah. All right, I'm done. So I've explained to you how watt meters are used and how you can use 2 watt meters, which is the standard industrial practice, in order to calculate the average power of any 3-phase load. It's simply just adding up the results of the 2 watt meters. And in a balanced system, you could figure out the power factor by simply using the readings from those watt meters. All right. So when you go get internships, literally you're just going to be connecting these things. Well, that's going to be a small part of your job. But if you're working with the engineering design team, trying to figure out what kind of feeders and all that kind of stuff you would need, this is a large part of it. Next time I'll try to, so for next class year, I'll have to write down notes instead of just going between 3 textbooks, because I was up until 11 making lasagnas, but whatever. I hope so. 3, yeah. So today I am providing lunch for Dr. Corbett's FYE. No, not FYE. Or no, engineering 120 series class things or something like that. Yeah, well, faculty takes turns. And I decided to make lasagna. Do better. I don't know. So, your exam is on Tuesday. I'm not going to put any of this on the exam. If I take that back. If I do, it will be a bonus question type thing, much like I did with maximum average power transfer. So I have mentioned now that this might be applicable for a bonus question. And I also mentioned that unbalanced delta Y transformation might be a good bonus question as well. Yes. Just 3-phase. Yes. Nope. So same rules as last class meeting, or excuse me, the last exam. You're free to use an equation sheet, 1 page, front and back, handwritten, whatever you feel is appropriate to put on there. Works for me. You'll turn it in with your test. Huh? Nope, you can do 2-sided. Doesn't hurt my feelings. If anybody has any questions, feel free to ask.